Okay. Okay. Welcome to the second part of the quantum computing session. It's my great pleasure to introduce John Martinis to you. I think he's the key player and founding father of superconducting quantum technologies. And actually, I'm following his work since the early 1980s when he was doing his PhD thesis in John Clark's group at Berkeley. And the title was Macroscopic Quantum Tunneling in Josephson Junctions, I think. So he's really doing quantum since the beginning of his career. After his PhD, he went to France to do a postdoc at Saclay and then joined NIST in Boulder. And there he initially worked on Coulomb blockade, squid arrays, so the classical Josephson technology. And then early in 2000, he began his effort to build a quantum computer based on superconducting circuits. He then joined University of California at Santa Barbara in 2004. And then in 2014, he joined Google quantum AI team, where he was heading the effort of Google to develop the first practical quantum computers. I would like to mention that in 2010, he received the Science Breakthrough of the Year Award of the American Association for the Advancement of Science. And in 2014, he received the prestigious London Prize, provided by the low temperature physics community. Okay, John, I think today you will talk on quantum supremacy. Welcome here in Munich. It's very bad that we cannot have here in person. I remember the last time when we were visiting this wonderful beer museum, and you have always take care about not pushing your head to the ceilings there. Okay, go ahead with your talk.
Yeah, thank you very much. It's great to be here. And good morning from Santa Barbara. So today I want to talk about our quantum supremacy work we published at the end of last year. And kind of the purpose of this is that to do a demonstration about quantum computing. People have been talking about the power of a quantum computer for many decades now. And what we decided to do is to get together the technology, get things working, to actually show that a quantum computer can be powerful by doing a calculation, even though it's crafted and not really very useful, but do any calculation so that when you had to check it with a supercomputer, it would take much longer to check it on the supercomputer than it is to run that. And there have been a lot of great interest, I would say, by industry, who now no longer see this as some, physics pipe dream that someday in the future we're going to maybe build something, but they can see, okay, this is really coming now. And of course, we have a long way to go. We have many more things to do, but people can see that, hey, this is something that really might work. So to get to quantum supremacy, we had to make our qubits better. And of course, we demonstrated quantum supremacy, 200 seconds quantum computer, checked a very long time. And then the key to all this is we're doing this computation on this huge Hilbert space, because that's where the power of the quantum computing comes from. And besides just demonstrating this, we can start looking inside of a quantum computing and kind of understanding what's going on in errors and checking the science models. And the nice thing about this is we don't see any further dirt effects or bad science, bad phenomenon that would say that you couldn't build a quantum computer. Everything looks good. Of course, we have to keep improving things. So here is the Sycamore processor for the quantum computer. It's a square array, tilted rectangular array of qubits on the left there. They're in the gray X's. So it's a 2D array, nearest neighbors, forward compatible to the surface code, doing error correction. So we built it that way in order to build it in a realistic way that we needed. And then what was new in this is in the bluish color, we have adjustable couplers between the qubits. And that's what's new here and enabled us to get this to work pretty well, and I'll describe that in a minute. The picture on the right, you can see the carrier chip. It's about 1 centimeter in size or so, and then we bump bonded another chip on top of that, which contains the qubits. So these couplers and qubits, we use the bump bonding, the two sides of the chip to get that to work properly. So we fabricate the chip, and then we put it on a circuit board, you see in the bottom left, with magnetic and electromagnetic shielding, with a bunch of microwave connectors on it. And then on the right, we put it at a dilution refrigerator at 10 millikelvin, and then connect many, many wires of that to do the control and readout of the chip. And a lot of getting this to work is getting lots and lots of wires to work reliably and in concert and properly. A big part of that is the control electronics. So those wires snake up the refrigerator. You see them on the right coming out and going to, on the left, the racks of electronics. And this is where we use a giga sample D-to-A converters and microwave mixers to make the microwave pulses and the like. So it's custom built, high speed, high precision, and dense enough so that we can control these many. Okay, so let's go on to the interesting physics of what does the actual qubit looks like. And when you look in the lower right, we have the circuit diagram of the device. So we have used transmod qubits, which are just nonlinear inductor capacitor resonators. And those are capacitively coupled off resonance to a transmission line resonator, and with an input and output that gives you readout of the qubit. And this is all very standard. And then in the center in green, and our qubits are frequency tunable. And that allows you to have an extra level of control to get everything just right. And you do that by putting in a DC current in the reddish line that puts a flux in the loop and changes the inductance and changes the frequency. And then what's new is in the green with these couplers put between the qubits. And that's just another transmon circuit that has an oscillation frequency higher than the qubits. And we off-resonantly couple one qubit to the other through this other transmon circuit. Now, since we're coupling the qubit signal below resonance of this green circuit, the net effect of that is a negative capacitor, okay? And that negative capacitance can be tuned by changing the frequency of the green qubit, again, with another line there. And then what you do is you add a physical capacitor across the thing, given by this coupler, which is a positive capacitance. And then if you tune the transmon, green transmon properly, the negative capacitance adds to the positive capacitance, and you can get a zero net coupling. And then, of course, you move away from that, and you can get even positive or negative coupling. So the way to see that the coupler works is on the left-hand side. And at the top, what we do is we put the qubits at the same frequency. And then we initialize, we put a photon in one of the qubits. And then we turn on the couplers and put them on resonance for a certain amount of time with certain coupling strength. And then afterward, we measure. And of course, if there's coupling between the qubits, you expect swapping of this excitation. And that's what you see in the blue color plot of the population popular transfer. And you see versus the coupler bias on the horizontal axis, you see oscillations in the vertical time axis. And you see on the left and right side, there's no oscillation at a certain bias, which is where the coupler is turned off. And then when you move away from that, you start seeing the oscillation, and then you coupler turn on. So on the bottom, you can see that we have a nice off condition with the coupler bias, and then we can turn the coupler bias on and get something like 40 megahertz coupling. So we have a large dynamic range between off and on. And of course, besides just turning the coupler off and on, we can move the qubits with different frequencies So you allow a lot of control, a lot of on-off ratio, and this really helps when you build a complex system to get it to work properly. So first thing we do is test whether it's working. So we do 1 and 2 qubit gates. And the plot here on the left shows in the black shows for a single qubit gate. And if you do an isolated single qubit gate, you get about 0.15% error. So that's an error almost in about 1,000 gates or so. And you can see in the integrated histogram, there's a distribution, but it's fairly tight. It's not unreasonable. But of course, the dotted line there is taken with individual gates. But what we want to do to run a real quantum computer is we run all the gates in parallel to make it faster. It's like how regular computers work. So we also take this simultaneously, where we turn off all the couplers and then run all the single qubit gates in parallel and do their benchmarking. And what's nice is when we do simultaneous, it's almost as good as with the isolated, okay? Which is good. You need to run this in that way. You can do the same thing for 2 qubit gates there in simultaneous. It's a little bit worse, but still acceptable. And then we also show the readout errors, which are a little bit high. There's things to fix in this chip that has been worked on and fixed since then. So these are good numbers. They allow you to run complex algorithms. And importantly, the simultaneous measurements say that you can do complex operations in parallel, which is of course what you want to do for a real quantum computer. Just quickly note that these kind of couplers allows you to have a very general coupler, Hamiltonian, coupling them, that has both SWAT terms of arbitrary magnitude, and also you can couple the 1-1 state to the 0-2-1, 0-2, or 2-0 virtually, so that you can get a control phase. And what's nice is you can operate this device in various ways, and able to tune how much swapping and how much, or I-swapping, and how much CZs you get. And here's an experiment. We put this on the archive where you can have full control of that. And the errors for doing this is actually very comparable to what I showed you before. So, and this is very nice because these are excitation preserving unitaries, which is, for example, what you want for fermiomic simulation. So that really helps you. And of course, it operates precisely. Okay, so in the quantum supremacy algorithm, what we're doing is actually running a general purpose algorithm, which is interspersing single qubit gates with 2 qubit gates, and of course between the nearest neighbors. And this is the general kind of sequence, algorithm sequence you would do for running any problem, okay? And what you can see here on the right is kind of the time sequence where we're doing single qubit gates and 2 qubit gates with the nearest neighbors rotating around to the various nearest neighbor gates. And if you look at 1 qubit in the center, which is on the bottom there, you can see how the sequence is. We have single qubit gates, and we have these 2 qubit gates that I talked about. On the very right-hand side, bottom right, you can see the single qubit gates are about 25 nanoseconds in length, comparable to what people do with transmon devices. And the 2 qubit gate is actually faster than that, which is kind of nice. Not necessarily essential, but it's good that it's faster. And we just put in essentially DC controls to do that. And you can see in the particular quantum supremacy, we're doing square root x and square root of y, which are in 90-degree rotations, but we can do non-Clifford rotations too with the square root of w, which is just it's the block sphere rotation axis between the x and y axis. And that is going to be the algorithm for quantum supremacy. So the validation algorithm, quantum supremacy, this is what's nice, this checks a general purpose circuit. So if you're going to run any algorithm you want to do, quantum supremacy is a special case of whatever you want to run. You can check how well it's doing it. And the basic idea in quantum supremacy is you use a randomly but known with chosen gates, and you would expect, maybe pseudo-classically, that you would get all the possible output states. But what happens is you get qubit speckle, where some of the probabilities are higher than some of the other probabilities. It's like a laser speckle going through diffused glass. And what you do is you measure which are the bright states, which are the higher probabilities. And then when you measure those probabilities by measuring the most likely states, and you check that to see if it matches the qubit speckle. And that's how we get a fidelity, and that's how we know everything's working right. So you have a circuit on the left, you run it through your quantum processor, you get certain output states of the 53 qubits, okay? And then to check it, what you do is you take the same circuit that's all calibrated, and then you know what that is, you run it through your supercomputer, and you get the probabilities, and then you do this cross entropy where you take the states that you measured, and then you look up what the probability for that state was. And if it's flat and uniform, then the probability is going to be 1 over 2 to the n, and the fidelity is going to be 0. But because for the quantum machine is going to measure the highest probability states, that'll be slightly higher than 1 over 2 to the n, and then the fidelity then will equal to 1. And if it's perfect, and then you know that the quantum computer is working right, and 0 if it's not working right. And the interesting thing here is if you just have one error, like a bit flip or a phase flip, you will get fidelity as 0. So you have to get everything right. You have to do things as perfectly as you can to see a signal, okay? And that's great because it does a system validation. Did you calibrate right? Is everything really working right when you're doing the whole thing? And then you can also use this, in fact, to learn the control mech, and I'll come back to that. Okay, so here's the data. We have random circuits. We run it from, in this case, from 12 to 53 qubits. This is for 14 cycles. So for the 12 qubit gates, that's about 250 gates total. So this is a reasonable number of gates for what we're doing now. And if we do that, we see a good fidelity signal of about 40%, okay? And that kind of makes sense because we have errors in the percent, fraction of a percent, and 250 gates, that makes sense. And then as you increase the number of qubits, keep the number of cycles the same, you have more and more gates. And of course, there's more and more chance for you to get an error. And you expect it to exponentially go down. And if you plot on a log scale, you see it's more or less aligned. And you see the fidelity go down as you expect. And at, 53 qubits, you're doing thousands of gates, 1,000 gates or so. And you still get a statistically significant fidelity that's not equal to 0. And we, you kind of see it's working. Now, in order to check this, okay, we do a variety of things. And we can, in fact, check this here with quantum supremacy algorithm, classical verification. The last data point takes 5 hours, so it's hard to do, but you can do it. Now, you can check this by taking your first circuit, which are the red circles, and then taking your circuit and just cutting the gates right in the center so that you have 2 isolated patches now. Okay, now that's exponentially easier to simulate, so you can do that easily. And if you look at the data for the patch circuits, which are the blue crosses, that more or less follows what you see with the red circles. And this makes sense. The number of gates are roughly the same, so the error is going to be roughly the same, and that's what you see it. And then you can do something in between where you start adding a few gates between them. So they're connected, they're entangled still, but it's actually easier to calculate using some nice computer tricks. And that's the green crosses, and again, it follows you. And then finally, what you can do is you can predict what you expect from the errors that we made with 1, 2 qubits and 2 qubits. Of course, it's not obvious that everything would work well when you have a lot of qubits, but you can at least check that. And that's the black line. And that, again, corresponds to the data very well. So this is good. Everything seems to be working. You build a very complex system, much more complex than your single or 2 qubit gates, still works well. Now, to do the quantum supremacy, what we then do is we can increase the number of cycles. And the second thing we do is we use a slightly different sequence of coupling the 2 qubit gates, because it turns out on the left, you can play some mathematical trick and make it easier. But when you go to the right-hand side, it makes the computer problem much, much harder. And we no longer have the red circles anymore. It's too hard to do. But what we can do is we can go back to the patch and elided, which are simplifications we can then calculate. And in that case, we see a nice exponential line, as we expect, when we see it agrees with the black line, kind of agrees with the back line. So because of the proxy of these equaling what we would see for the red circles, we, of course, strongly suspect that if we can actually do the calculation on the right side, it would lie over the other data and be fine. And just to note here, the plus and minus 5 sigma error bars are shown there, and the fidelity of the system is significantly different than 0. So we know, you know, some fraction of the events we're really seeing this probably work properly. Now, given that, I want to talk about the important quantum science results here. Okay. Besides, okay, it works, it does a hard computation, great, but there's science here, okay? And I want to make the point here that we got the same fidelity with the full circuit, with the elided, with the patch, and the predicted. This is really kind of amazing because it means that the errors we measure do not depend on the amount of entanglement and computational complexity. Okay, now we expected that, okay? That's what's predicted from quantum science, but it's really amazing to see that happening in an experiment because, you know, a lot of things could go wrong, okay? And I think things were designed well enough with low crosstalk and whatever that happened. Kind of looking at that a little bit closely, we don't see any new decoherence physics, okay? The probability prediction is just the fidelity is 1 minus the product of 1 minus the errors of all the individual processes. It works well. And the fact that, again, that it works well, no new decoherence physics is a really good sign that we expect, for example, error correction to work. Of course, we have to test it. There's some other things that might go wrong, correlated errors might go wrong. You have to check that, but it's a really good sign. Thirdly, of course, this is hard computation because of the enormous Hilbert space, 10 to the 16 Hilbert space. So it's been previously tested to about 1,000 Hilbert space, and now we're up to about 10 to the 16. And so we experimentally tested that quantum mechanics works with a larger Hilbert space of 10 to the 13. Okay, so in physics, there's a long history of exploring the boundaries of when's physics still work. So this, we think, is a pretty interesting and significant test, and of course, what you need to have a quantum computer be useful. Finally, let me just say, there's some interesting, you can look inside this in an interesting way, and you can kind of test this model of digitized errors. I want to show on the right here, I have a plot where I just took one gate, one Z gate, or phase in the gate, and comparing it to, in the quantum supremacy, I changed the angle of the simulated gate from 0, which is what we programmed into the quantum computer, you know, all the way through to 2 pi. And you see, when you look at the cross entropy fidelity, in fact, the fidelity goes from, what, 20% or so, all the way to 0. It goes to 0 when you have a pi theta or a phase flip. And this verifies the fact that if you had any error anywhere in the circuit, the fidelity goes to 0. And in fact, if you look at this curve, it's a cosine squared theta over 2 curve. This is exactly the curve that you would expect if you want to digitize errors. And you just say, okay, what's the projection of that particular gate rotation error on it? And it, again, agrees very well. And this is great because I've always found it amazing that this digitized error model works so well in terms of, showing what happens in quantum mechanics with errors. And here's some more direct proof that error works in the middle of this complicated calculation, okay? You can kind of understand it, intuitively understand it for 1 qubit, but in the middle of a big things, it's not necessarily so. So it's tested and it works, and that's great. Okay. Before I summarize here, just let me show some recent results. Here's a paper by the theory group on the Sycamore device that's been posted, and it's working its way through reviews, so people will see the full final results soon. And it's doing quantum chemistry, okay? And that's what the chip is designed for. So in the way to use the chip, of course, you have to compile the chemistry to qubits, which is a known procedure now. And you use Hartree-Fock, fermionic operators, second quantization. We have a coupling sequence with swaps, and then we do some suite of measurement. And that's given on the circuit diagram in figure 2. In fact, it's for H6. We've done more complicated than that. And then what's amazing about running this circuit is that you can correct imperfections. There's a certain symmetries involved when you measure it. And it's amazing in this algorithm, by doing the correct measurements and doing everything right, you can improve the fidelity of the circuit by over a factor of 100, okay? And using these symmetries and looking at the measurements and correcting for that. And of course, you do the variational optimization of thetas. So with the improved processor, with a lot of qubits, with good fidelity, and this clever algorithm, we can now run complex simulations. So on the right-hand side, you see a hydrogen-12 molecule simulation, and you see the dip corresponding to the binding. And on the little inset, you see the errors. It's not quite at H12. It's not, at the chemical accuracy, but it's very reasonable. But it's a very complicated molecule. And of course, this is this is what we consider like a benchmark molecule, simple enough to kind of show that everything's working. This is double the number of qubits or electrons than what's anyone ever done before. It's the largest chemistry simulation to date. And it has more than 10 times the number of gates that anyone's done before. So with the better processor, with the circ to program it, with open fermion to do all the chemistry to qubit calculations, we have a very nice system to do quantum chemistry. And of course, there's many other things to do. I just want to show that the Sycamore device is not just some special purpose science device. It's really practical, and I will be able to do things with it that are interesting. So at this point, I'm just going to wrap up and just say, in quantum computers, performance matters greatly. And we think that this is a breakthrough device in the Sycamore, and there's more things to fix and get better, but there's a lot of important things that were fixed here. So there's a nice future here. And okay, we have this supremacy algorithm, and that does something powerful, and we're hoping, well, maybe someone out there very clever will, it's just one idea away from some compelling application. We'll have to see. But it's a really interesting time for this technology. And with that, I just really want to thank the very large team at Google, both in LA and especially in Santa Barbara, who got this to work. There are many, many things that had to get improved and fixed here, and it's only by the team effort that happened. Okay, thank you.
Yeah, thanks, John, for the great results. I would like to ask Stefan now whether there are questions coming up during the presentation.
Yes, I have the first question. Why do you prefer quantum supremacy to quantum advantage? That was the first question by the audience.
It's a matter of words, okay? We can discuss and argue over words and wordsmithing a lot. First of all, quantum supremacy was first proposed by John Preskill, and that is fine. Unfortunately, the word supremacy is not. It's kind of edgy right now, so that's bad. The other thing is quantum advantage kind of gives a connotation that the quantum is a little bit better than classical, whereas in our case, when it's 300 seconds versus 10,000 years, that sounds a little bit more than advantage to me. So that. Now, I understand there might be other definitions of this concept, and maybe it's good we have two words. But yeah, that's kind of why we decided to stick with that. Again, in the end, forget about wordsmithing, 300 seconds, classical computing, much, much longer, okay? So
okay,
that's what we did.
Okay, great. I forward the next question. What is the limit of the number of qubits you can implement on one chip with the current technology?
I think we can scale up with this basic idea to at least 1,000, and I'm going to say 10,000, and then we have ideas on how to scale that up to 1 million. And I've been working on wiring for 3 or 4 years now, and I know how to scale up to 100,000 or 1 million. And the hard part, which was making sure you can make an array and adjustable couplers, a lot of work went into that. And the fact that we have low crosstalk, so that we can do this, basically means that the way we scale is working properly. Now, of course, to wire this up properly, you have to invent things, and that's what happened. And we'll see if that can be fielded.
Okay, next question from the audience. As I understand, you said that the Sycamore device is built specifically to program quantum chemistry problems. Why is this chip so well suited to this?
Yeah, that's a good question. Well, it's well suited for running general algorithms. Of course, it's only 2D connected. And we understand people would like to have all connected, but that's kind of, you're never going to get all connected when you have thousands or millions of qubits, okay? But 2D works well. And, but I would say it's well enough connected that you can run reasonable algorithms properly. And then it turns out to run the quantum chemistry, you only need a 1D chain. So we just kind of snake the thing into this. But clearly for more complex algorithms, you would use the full 2D connectivity. Mostly I wanted to say there is that this is not some special purpose chip for doing quantum supremacy. It's upward compatible to doing surface code, doing error correction. It's upward compatible for doing NISC. Of course, you have to fit it into the device. And now we get to see with experiments, how well that will work.
Okay. Actually, I have many more questions. I think maybe we take 2 more because we started a little late. Could you please comment on why you're using DC pulses for 2 qubit gates? Has some work being done on using machine learning for pulse optimizations?
So yeah, there's a big, kind of philosophical question on people. Do you use microwave gates and do you use DC gates? And, we understand, of course, that DC gates are a lot harder than microwave gates because you have tails and other things that go wrong. But the nice thing about DC gates is you can change the qubit frequencies. And when you do that, you can really turn on and off the couplings very effectively, because it's not just having the couplings on, you have to turn them off. And we just find that's a very effective way of doing that. So, you know, not everyone uses tunable qubits. We understand the coherence is lower, but, you know, if you can make a, what was it, 12 nanosecond 2-qubit gate by using DC pulses and really turn it off, okay, that's a huge advantage. And I would say that our group spent like 10 years trying to figure out how to use and calibrate the DC gates well. So it's harder, but you get more performance, especially you get fast gates. You really want fast gates. Okay, you get so many advantages from fast gates.
Okay, great. Actually, I think I'll postpone the next question together with the other ones that are in line to the roundtable discussion. So okay. I hand back to Rudolf.
Great, that'd be fun.
Yeah. Okay. Yes, that's a good idea. And I would like to ask Anka to put the link to the roundtable discussion into the chat. Then everybody just could click on it and easily find the roundtable discussion. Okay, thanks a lot, John, for the wonderful talk. And